So good afternoon. I think that it's 4 o'clock and we can start this session. That here in this session, sorry, is okay now? Okay, sorry. So we can start the session about monitoring.
On the stage.
Sorry. I was saying that we can start the session about monitoring advanced infrastructure, such as the one using in the CERN or the one that I use with 10 gigabit links or cards in the PC. So our first speaker comes from the Edinburgh Parallel Computing Centre. He is working primarily on large grid infrastructures projects such as EG and DESA. His name is Jeremy Nowell. So, please.
Okay, so I'm going to start the session off with a talk about the work that we did in the EG project over the last couple of years, particularly the network monitoring for the EG grid. So this work was primarily done in Edinburgh at EPCC, co-funded by the European Commission through the EG project and JISC, the UK Funding Council. The remote to work. Here we go. So this is the overview of my talk. I'm going to start with a brief introduction to EG for those of you that don't know it. Say something about why I think network monitoring is important for grid infrastructures. Some of the requirements that we got and the challenges of applying monitoring to the grid, the strategy that we applied and the architecture of what we developed, the tools produced, and then some of the challenges. So the EG project, I'm going to talk about the work that was done in the first two phases of this project. So EG itself started 1st of April 2004, 71 partners. Then that went on to EG2, 92 partners in 32 countries, split into 13 federations around Europe. So the objectives of EG are large-scale production quality infrastructure for e-science. That's the main objective, obviously. Part of the EG project develops middleware called G-Lite. So during EG2 particularly, the emphasis was on improving and maintaining the middleware, and also attracting resources into the grid from industry as well as other areas of science. So this is a kind of general EG publicity slide. The yellow dots show countries involved in the EG infrastructure, so it's not restricted to Europe, it's actually all over the world. There's several different collaborations with other grid projects as well. So 250 sites in 50 countries, large number of CPUs contributing resources to the grid. Over 150,000 jobs per day, and quite an interesting point, there's 200 virtual organizations involved, so a lot of people might think of EG as just high energy physics, but there's actually now very many different areas of science involved in the EG. So why network monitoring? And why network monitoring for the grid in particular? So, probably preaching to the converted here, but we'll go through this anyway. So, obviously, it helps us diagnose performance problems between different sites in the grid. So, you might be transferring some files. Why is it particularly slow at the moment? Is something broken? Is it a network, a particular server on the grid, or the grid middleware? I can't see a particular site on the grid, but does that mean the network's broken, or is it just that site that's had some kind of problem with the machine? Quite a famous one, the application's performance varies with the time of day. Is there some kind of network bottleneck somewhere? When we're talking about grid infrastructures, I think this next point is quite important, that monitoring applied to the grid actually helps diagnose problems within the site and not just on the NREN infrastructure, let's say. So a lot, in fact, probably most network problems that are seen in large infrastructures are the last mile issues, so the problems within the site. And finally, obviously, it helps if you've got data available from operating your grid to help future decisions on provisioning more network bandwidth. Yeah. So, what's particularly different about network monitoring when we apply it to the grid? Clearly, the grid is the base layer, if you like, of the network is the base layer of the grid. If you don't have a network there, then there's no grid. Grid, by definition, is kind of distributed computing. So grid applications quite often transferring large amounts of data. If you think about the LHC, then they're going to be transferring data almost continually over this 10 gigabit dedicated network. So multiple different connections and streams. And also, grids have been early adopters of new technologies, so provisioned light paths to give dedicated networks. And what's crucial is that the end-to-end performance, as was mentioned in the plenary session earlier, so it's okay saying I've bought a 10 gigabit network, my application's just going to go at 10 gigabit, but that's clearly not the case. So this is quite a good slide, I guess. Borrowed from someone else, it has to be said. So one thing that people ask when it comes to networks is, well, my application's going slow. It must be the network that's the problem. Why don't we just provision some more bandwidth? So bandwidth is actually, if you think about it, a bit like a drug, like a narcotic. It gets very addictive if you're not careful. You start with a little bit, but that's not really good enough for your application's performance. So you buy some more, you increase the dose a bit, but that's never as good as you think it's going to be. So you keep on buying more and more, hoping that the bigger dose is going to make your application perform better. So you can go on buying more and more bandwidth, but your application is never actually going to run as well as you think it would do from the bandwidth that you've provisioned. So as I said before, this is probably because most problems are in the campus network, your end system, and so on, the application. So some of the issues that you have to think about, end system issues, the network interface, the TCP stack they happen to be using, the operating system, so on. Infrastructures around the network, old network equipment on the campus, let's say, security restrictions, firewalls, protocols, all kinds of things. And then, obviously, you've got lots of people using the network, so they're all going to interfere, possibly cause congestion. So, network monitoring can help, and it can help in the operations of the grid, because, hopefully, you choose your network monitoring tool so that you have the right metrics available to you, and then you can make better decisions. And importantly, it lets users see the performance that they should be getting from their application. If you're doing proper end-to-end monitoring, then instead of just thinking, I'm going to get 10 gigabit, then they can say, oh yeah, I should be getting 100 megabits from this application, true end-to-end from one machine to the other. And also, of course, we can identify faults and problems in the network and help to solve them. So having historical network data available to you can often be of benefit to the whole site. So if you're running a contributing resources to the grid that happen to be doing network monitoring, then they quite often can show up strange configuration problems on your site that local network admins never knew existed. So right back at the beginning of the project, we gathered requirements from different types of users, network operation centers, grid operation centers, and so on. Won't go into too much detail on these, but you can see that quite often they needed a web-based GUI to investigate problems, possibly some alarms when metrics go out of where they should be. The ability to run on-demand tests, possibly, have historical data available, and also have the data there for backbones and end-to-end. There's also requirements coming from service level agreements. So with grids now, you're seeing the beginning of SLAs, so that you set up a premium IP path between two different sites to guarantee your application performance at a particular time. So there's requirements to monitor that performance and make sure that the path that you've provisioned is actually delivering according to its SLA. So obviously in a case like that, then you need quite frequent measurements, say at least every 10 minutes, to be able to be sure that you're getting what you asked for. So I won't spend any time on that, but you can just see kind of this is a summary of the different types of metrics that people asked for. So the usual kind of achievable bandwidth, packet loss, round trip time, and so on. So some of the challenges particular to the EG infrastructure, obviously we saw before it's a huge infrastructure, hundreds of different sites. So you can imagine that all these sites potentially have different ways of collecting network monitoring data. Said before, there's the two different types of measurements, end-to-end data and the backbone measurements. There's hundreds of different measurement tools that we could use, different data formats and so on. In EG2, there's the different federations that I talked about, but also there's different domains within those federations, so everyone's responsible for their own resources at the end of the day. So you're crossing administrative boundaries when you're running applications on the grid. So the strategy that we adopted quite some time ago at the beginning of the project was to standardize access to the network monitoring data. So there's hundreds of different monitoring tools available, so we're not going to set out and develop new ones. There'd just be no point in doing that. But instead we're going to facilitate access to data that already exists or that can be collected by these different tools. So the way we did this was to use a standard that's developed in the Open Grid Forum, previously the Global Grid Forum, GGF, and now OGF. There's a working group within there, the Network Monitoring Working Group, Network Measurements Working Group, sorry. So they've produced schemas for representing network measurements that hopefully we can adopt and have access to different network measurement data. And if such interfaces are not developed, then we can develop them. So a schematic diagram of the situation, we have our end users at the top, be that the network operating center, the grid operating center. And then at the bottom we have different monitoring frameworks, so Perf-Sonar, say, or our own monitoring framework. And in the middle we have the stuff that we're going to develop to give access to the data. So this is the architecture that we ended up with, we ended up developing. So first we have a user interface, what we call the diagnostic tool, which is a web-based application that allows users to select different network paths, the metric that they're interested in, and then plot the results. At the bottom, we have different measurement frameworks. So the two we concentrated on for this were Perf-Sonar for passive utilization data from the backbone, so from Giant2, for example, and E2E-Monit, which is our own framework for gathering this important end-to-end data. And then in the middle is our key piece of middleware, if you like. So this is the single point of contact for clients. So obviously you have a client, you don't want to have to configure that all the time to talk to different measurement frameworks. You don't really, as a user, want to care where those frameworks are located. So the client instead contacts the mediator and is able to do metadata discovery, if you like. So it's able to find out which frameworks are available, which network paths it can see, what data is available for those paths, and so on. And then finally it brokers the data requests to the different frameworks. So that's the architecture complete, so diagnostic tool, mediator, and then the frameworks. All the measurements, all the data that's exchanged between these different components uses the NMWG schema that I talked about. So hopefully it makes it a lot easier then to bolt on different measurement frameworks at the bottom and potentially develop different clients at the top that can talk to our mediator. So in terms of the metrics available to you, then clearly that just depends on what measurement tools you're going to use. With what I've presented there, the possibility is there to support access to any network data that you have, provided it's available in this OGF compliant schema. So E2E-Monit that I've mentioned supports 3 different common measurement tools: ping for round-trip time and packet loss, iPerf for your TCP achievable bandwidth, and UDP-MOM for UDP measurements of achievable bandwidth, one-way delay variation, and so on. And then Perf-Sonar, developed by Giant2 and others, and that's giving us the backbone data. So this is an example of the diagnostic tool that we developed, the web application that users actually get access to their data. So it's available through any browser. We have a possibility to restrict access to it using standard X509 certificates if you want to protect the data. So you can see, you run through there, you select different paths and come back down to select the metrics that is available for a particular path. And then you get your results. So here this is achievable bandwidth measured using iPerf, or available bandwidth estimated using UDP-MOM. And then that's finally an example of utilization data from Giant2. So that's just a summary of the things that we've produced. So clients, the diagnostic tool, the mediator, and then the different measurement frameworks. So the tools that we've developed facilitate access to the data. Okay, in actual fact, they're only useful if you have data available. So, providing that facility to federate different data from different tools is clearly not enough by itself. And the strategy that we adopted a while ago was to use measurement data that is already collected. But what we actually discovered is a huge problem is that such frameworks up to now have really not been sufficiently deployed across the sites. So you could say that everyone should deploy E2E on it, but that could give you huge problems in terms of scalability and so on. So ideally you would want, say within an EG framework, the different federations to make their own deployment decisions. So an example of where this has happened is in the UK, where most of the contributing resources for EG come from the Grid PP project, and they've developed a tool called GridMon, which collects similar kind of data as E2E Monet, but that's deployed now, and they'll be making their data available through the NMWG schema. So we could, in fact, plug our tools just into that and gather their data, make their data available. Deployment of the tools themselves is not easy. So E2E Monet, let's say, has to be a clear benefit to the site before they even think about doing this. And often that benefit is not obvious to a site or a system admin until an incident has happened, by which time it's too late. So have you any network data available? We saw some problem last week. Well, no, because you haven't bothered installing the tool yet. So what we actually found was that the tools need to be almost trivial to install. Sysadmins are very busy on the EG grid maintaining different parts of the middleware. The network is the thing they probably worry about least. So you need something that's just going to install and maintain itself almost. And also, when you start talking about end-to-end measurements, then you really need to think very carefully about scheduling them carefully. If you think about a project such as EG, if you set up a meshed infrastructure between all the sites, then clearly that's going to be ridiculous. 250 sites all running network tests between themselves. You're just going to run out of bandwidth just by testing the network. And we also found that different user groups have wildly different requirements for data. So site admins in particular just want an alarm, and they're never actually going to bother looking at the DT. And one problem that you still run into now a lot still is that the network is still assumed by many just to work. It's just there. We don't have to worry about it as grid admins. It's just going to be there. So one of the things we did within the project to address the issue of scalability of monitoring tools was to develop something called the Probes Control Protocol, PCP. So with the end-to-end tools that I talked about, typically these have been managed by cron jobs, which is really not scalable at all and causes problems with different time zones and so on when you're talking about a distributed infrastructure. So this is a mechanism for passing tokens between sites. So it ensures that you have this periodic execution of the tasks, but it prevents overlapping measurements. So a site is not allowed to run a test until it receives the token from the last site in the clique, if you like, the clique of sites that you're talking about. It's robust, so if a site goes down, then the measurement tool will still be run after some kind of timeout, and it's also secure. So this is a brief schematic. I'm not sure I have time to go into this into too much detail, but essentially you have a delay set up between when you want a test to run at different sites, and then you have a period, so between the same tool running at the same site. And then moving on to the information for site admins, the strategy that we adopted there was to use something that's been developed more widely for monitoring within EG in general, which is Nagios, which is a tool that's used by different sysadmins. So the idea of this is that the sysadmin has a single view of all their services, and one of the pieces of information that's made available to them is on the network. So at the moment, this is just a simple TCP connection, and we did this using data from the EGE network operating center that run the tests for this. So you probably can't read that, but that's just a screenshot of, say, one site, all the different services that are available, and one of those is the network. So a few conclusions then. So we've demonstrated federated access to network measurement data through the use of the OGF schema. And I think that's now a solved problem. We are able to access data from different measurement frameworks, and that would be quite straightforward to adopt other frameworks as desired. But the problem that we encountered is that actually getting the data itself is much harder. It's a huge deployment challenge still to solve, really. And there needs to be a big job to sell to sites the value of having this data available. And then just as a kind of challenge at the end, should projects such as EGE be attempting to do their own monitoring at all? I'm not really going to answer that question, but if they don't do it, who else will? Maybe the network providers are going to do it, but then you're not going to end up with the important end-to-end monitoring that I talked about. You're going to end up with end-to-end between different sites, but not between different machines at the sites, which is really what you care about when you're talking about application performance. And then finally, what happens if a site happens to be in two different projects or many different projects? They're all doing their own network monitoring. You're just going to run into problems. So that's a question to think about for the future, I think. So I'll leave it there. Okay.
Okay, thank you. Is there any question to Jeremy? No? Okay. Thank you very much. Then we will... thank you. Then our next speaker, his name is Ryan Martin. He is a senior electronic engineer working for more than 30 years at CERN. Currently, he is leading the team that is working on designing, commissioning, and monitoring the data network for the Atlas experiment that is going to be carried out in the LHC at CERN. So, thank you very much.
Is this the boost use? Okay. Good afternoon. Thank you. Thank you for showing up. My name is Brian Martin. I work for the Atlas experiment at CERN, and I'm speaking on behalf of this small team of, let's find the right button here, small team of people that's working with me. Collectively, we've come up with a lot of good ideas for network monitoring, which I'd like to share with you now. I hope you find it interesting. Those who are just doing email, tell them I said hi. Just a quick, put this in context. This is the footprint of the LHC accelerator on the background of Geneva down here in the lake. The accelerator itself is actually about 100 meters underground, and it's carrying counter-rotating proton beams, which are brought to collision at 4 specific points along the ring, and this is the one that I work in, which is Atlas. At each collision point, each experiment has got a different kind of detector. This is the Atlas one, shown in cutaway mode. Basically, it's a series of concentric detectors around the collision point. And this is a picture of the experiment itself during the construction phase. Those small white dots that you see there, those are the hard hats of people actually working on the construction. So it gives you an idea of the scale. Lots of big numbers here. The important one that I'm going to be talking about here is this one. This detector puts out 80 terabytes of data a second, every second, for every minute, every hour, for years. And you can't possibly cope with that amount of data. There's no way that you could put it. There's no way you could process it all. You have to cut it down to some usable number. And what happens then is we send the data through a set of filter algorithms in a few processors, where a few read several thousand. The network that we put together for doing the data analysis, I don't want to go into too much detail here. The yellow boxes are processors. There's lots of them. The brown boxes here, the round things, are edge aggregation switches. In this case, there's 10 gig links here and 1 gig links to local processors. And there's the red things are chassis cores. This part of the network is running at very high speed. Small selections of the events here are sent for consideration to the processors. They have a quick look at it and say, yes, no, maybe. And if it's a yes, then it has to go on to the next level. There's about 100 processors here which will then pull the full event out of the buffers here, send them through another chassis, and to up to 2,000 or 3,000 processors here for final consideration. And if they pass, then they're sent down here and finally off to the grid, which is perhaps more familiar territory for you. On top of that, each processor has its own housekeeping data, histogram building, please mother, I'm sick messages. And these go through redundant core chassis over a control network. And if that wasn't difficult enough, at the network level, we ourselves are doing switches all around the edge, which is collecting SNMP data from every single switch in the system, asking what is your status, what is the traffic, what is going on. Just looking at the diagram at this level, it's fairly obvious that it's going to be difficult to represent in any way because you have these series of overlapping fan-ends, which is difficult to represent in any number of dimensions. So it's going to be a challenge understanding what's going on here. To give you an idea of scale, up here we have the buffers, which is where the data is coming out of the detectors. This is just one of the detectors. There's 17 of them altogether. Here we have the aggregation switches in one of the processor farms. There's one for control and one for data. There's about 100 of these farms, as you can see over here. And in the center we have the switching cores, which actually handle all of the data. We have another problem as well, which is physicists. You can't escape them at CERN, they go with the territory. The network is dimensioned to meet some kind of sort of ballpark figure that they thought they were going to be putting out in data. So we built a network that would support this with a maximum link occupancy of about 60%. So you would think that as far as network support is concerned, that you could just sit back and relax. Actually, a 60% link is seen by a physicist as a challenge. They're all little Scotties at heart, you know, I cannot take it any faster, Jimmy. And they see 40% for free. And what they will do, therefore, is turn up the acceptance rate, i.e. turn up the wick until something breaks, which is usually the network, at which point they then complain that the network doesn't work. So we're looking forward to 10 years or so running continuously out of spec. And therefore we have an extra layer of work to do, which is to distinguish between real and self-inflicted problems. So we need monitoring for the normal standard things of malfunctions, but also to identify out-of-bounds behavior, find anomalous performances, and we have to break down the mindset that says, if there's any application, first blame the network. We have to establish a degree of confidence that the network really is working, and then turn it around and say, actually, we know things that you don't, and this can help make your life easier. The first thing to do if you're going to be monitoring inventory of this size is to get it in a database. Databases are wonderful, everyone should have one, and in Atlas just about everybody does. So the IP is delivered in one database, the equipment is in another database, the geographical location is in the third one, and the discovered interconnect is yet in a fourth one, and they're all put together by different people at different times, and the assumption is they're all the same. Well, of course, they're not. So we cross-check everything. When we first did this, I had 60 pages of difference. We're now down to about 2, so we have a reasonable degree of confidence that we're starting to look at something we know. On top of that, oh, that's interesting, it's disappeared. Maybe no, it'll be with us in a moment. We have the network itself is described in terms of network description here, which is done in a net design package plugin that we developed for Visio. And this thing that you don't see over here is the connectivity chart, which shows what has actually been discovered. And we compare the two data sources and keep the drawings up to date if changes have been made that are legitimate, or if we discover unwanted additions, we track them down and pull them out. The basic monitoring is done with a commercial tool called Spectrum. It has three main advantages as far as we're concerned. It handles heterogeneous switch support. Many vendors will sell you some kind of monitoring system which only works with their switches. It also has a nice tool for root cause analysis, which if you have a break at a central point, it only gives you the central point that's failed and not the hundreds of moaning messages from further downstream. And above all, it's used in our IT department, so we have a degree of confidence that it works. We poll for status every 5 minutes and for traffic every 30 seconds. This generates a huge amount of data. And luckily, Spectrum gives us the possibility of archiving it at different levels of averaging over time. We bought the version with 64-bit counters, which you do need if you're measuring 10-gig networks because you want to avoid the byte count rollover. It's a good solid workhorse. It has clear displays, mostly, some limitations. And you can get at the internal data structures through Corba, mostly, also with some limitations. This gives you an idea of how difficult it is, I was telling you, with these multiple overlapping links here. These are the processors that live between the very fast and the only slightly fast networks there. And they have about 5 connections each. And you can actually force them into something which looks reasonable. Until the day that they say, well, actually, we've got a naming problem here. We've had to change the port naming. So rather than edit every single instance here, you just remove the model, update the model, and plug it back in again, at which point Spectrum says, oh, I've never seen you before, and I will now auto-place everything, and you've lost all of your work because you can't lock the references. We're going to have trouble with describing this network anyway, we know that. And we need some data management flexibility. We can take advantage of grouping, either by affiliation or by network. But one thing we do want is to display the traffic as well, which you can't do on Spectrum, so we have to move to something else. This is the Spectrum plot here, and this is the way that we actually want our data to be shown in these various forms that are useful to us. And so we built ourselves a middleware, which is a set of applications written in Python and in Java, which add the data from our other databases to the traffic that comes from Spectrum, and then we can confect our own displays to suit us. And I'm going to talk about some of those now. The first one is a very efficient network browser. Down the left-hand side here, we have the hierarchical tree where switches are grouped into functional levels. And if you just click at the lower level on one of the folders of one of these switches, then you will generate automatically mini plots for every single port within the switch. This saves trolling through every port one after another, and you see both the traffic and the errors both automatically scaled. So you have a quick idea instantly, visually, over multiple ports, if they're all doing the same thing, all doing something different, and if they're all doing the same amount of the same thing. And I'll come back to that later as well. From this point, you can navigate quite easily to looking at the actual physical data that is within the switch in terms of the number of transmit or the number of receive bits. And you can also see the switch in a hierarchy of who's the busiest of the switches in the network. So you know that this particular one that I've done the plot for is about the 4th busiest in the system. And if you're wondering why it's so busy, you can also get a plot of all of the applications that are running in the processes around there. So you can do a mental cross-correlation. Oh, this guy's in there, that's why he's so busy. Or you can return back up the tree and go and click down on any of the individual ports, and then you get the standard traffic plots. So you have a temporal view of what's been going on in every port with the association of any errors that go with it. Coming back to the affiliated mini plots, these are very useful because in any affiliated group of devices, you'd expect they'd all be doing more or less the same thing, especially since you put a lot of effort into load balancing them. And it's fairly easy to see at a visual level, at least here, that these 4 are doing more or less exactly the same thing, and this guy is out to lunch doing something completely different. It might or may or not be a good thing, but at least it makes you visually, you're instantly aware of what's going on. Scaling it, however, becomes difficult. We're talking about thousands of nodes. 4 is just not going to cut it. So we have here a way where you can overlap all of the individual ones, and you can see that from this kind of aggregation that some of these guys are not pulling their weight, some of them are, and there's a reasonable distribution. So for one rack of processors, here you have just 30 instances. You have both the mini plots available plus the aggregation, so you see how any one person is doing compared to any of the others. You can only take this so far. This is a plot where there's only 4, and it's fairly obvious that this guy is not pulling his weight and these 3 are doing more or less. Kick it into 30 and it starts to get a bit of a blur. And especially, you don't see the guys that are doing absolutely nothing at all because they're along the bottom axis, hiding behind the axis line. So we've been experimenting with different ways of viewing this, and this is a 3D view whereby the amount of traffic is given a height and a color plot. And you can see, therefore, that by looking at it here, one guy is clearly not doing very much. Unfortunately, with 3D plots, it depends on the angle you look at it, whether you see it or not. And we find it's a lot better if you just actually look down on the top. And there you have the number of processors in this line. This is your timeline. These are the various different traffic colors, and this guy's clearly doing absolutely nothing whatsoever. And both these plots lend themselves to analysis by signal processing technique, so that's something we're going to be looking at in the very near future. When we bought these switches, or rather before we bought these switches, we characterized their behavior with a number of stringent tests. And we get the standard plot here of latency versus load. These are obviously chassis-based switches because they don't hit the knee until you're about 90-95% occupied, which means they've got really big buffers. And because of that also, you're not going to see any packet discards until 90-95%. So these are pretty solid switches. And therefore you can get the naive worldview that says, well, if they're that good, then I don't need to worry that much. So I can set a flag that says, well, here's my 60% operating point down here. Say I'm getting up to here, I'm stressed, and then maybe in this area I'm overloaded. So I can set flags for loads with high thresholds. According to this, I'm not supposed to be seeing any errors at all, so I can set a flag errors with low thresholds, say about 0.05%, which is this line there, which is 10 packets a second at a gigabit per second. And fortunately, it doesn't quite work like that. Here's two cases that show up. By the way, that's wrong. That should read TCP. Here's a case where we've got traffic running at 80% occupancy, and we're losing 5 kilopackets per second. Oh my God, the sky's falling in. This is awful. Well, it's not awful. It's purely a case of oversubscription. 60% is what the advertised accept rate is. This is the lunatic physicist turning the wick up, taking far more events per second than he threatened he would do in the first case. And this is TCP/IP saying, throw at me what you got. I can cope with it because I've got bandwidth to spare, but I will just use some of that bandwidth for retries. So the physicist is very happy. He thinks he's getting something for free, and he actually is, because TCP/IP is just covering up the tracks. He gets all of the events he wanted, and I've seen similar plots running at 100% and even greater errors, and nobody cares at all because they're all getting exactly what they want. This is not an error. This, however, is another case of oversubscription. We're only running at less than 2% of the load, and we've only got 10 packets per second. So you think, well, that's not a problem. 10 packets a second error, 2% of the load, no problem. Unfortunately, it is a problem. The reason it's a problem is this is in the high-speed part of the network, where you're only supposed to be running about 25 kilobytes per second from n different sources. The buffering is largely adequate for all of this. This is a critical area we went into in the design space. But unfortunately, one of the detectors is putting out 20 times more data than he's supposed to. He's filling up all the buffers, and what's happening is the other small fragments are being bumped out. If you bump out a small fragment, the chances are very high now that you're going to be losing the last frame in your series, at which point TCP/IP goes into timeout, which means that you're spending a lot of time doing nothing, which means all the Higgs particles are piling up somewhere while this guy is just doing a timeout. The event-taking rate drops down dramatically, and the lead physicist at this point is looking for somebody to kill. So this is a definite error. You also have things, anomalous traffic. This is a plot from a control link. And the human brain is very easy to pick up patterns. Here you have monotonic increases in traffic. which is going from 1% to 2% of throughput in just a couple of hours. You know intuitively this is not sustainable. You don't necessarily know why it's happening. You can have a good guess, but you know if they keep it up, it's going to hurt you. So from here, you can't go looking at plots every day of your life. I have been, but I don't intend to do it forever. So we'll be looking at a rules-based expert system that incorporates these kind of observations into the system. So far, we've concentrated on low-level port and switch monitoring. We've identified obvious scaling issues. But in this particular network, and like perhaps some of those you deal with, cause and effect are system-wide. Bad things happening at the top mean bad things happening at the bottom and vice versa. So I want to be able to see the complete system. I want to have an architectural model that is readable. I know what I've built. I don't want some auto-placement device putting things upside down. And I want to be able to put real-time statistics into it, which, as I've already said, we can't do so far. So we use the guess editor in order to take the data out of Spectrum and display it in a form that is overlaid with color coding for the traffic that we've mentioned. Notice that in this thing, we've only got the switches. We don't have the hosts. And the auto-placement problem here is that we get different, depending on the amount of resources that are switched on at the time, it will lay out differently, so it looks ugly and people don't understand it, apart from the experts who actually zoom down and say, oh, it's that switch, I know where this is, and it's, by the way, it's upside down. So we have a student who's actually discovered a way to use guess to force placement. Since the switches all have aliases which are relative to their function, you can define a start point and a growth direction in terms of the index of the name of the device you're using, and you can, in that case, provide force placement into something that makes sense. This is now our data sources. These are our two data control switches, intermediate processors, the pipe out, and over here we have the control network. And I was sitting there, and it was one of these luminous moments. I was sitting with a student placing this one because it was out of place. I thought this looked ugly, so could you please just move that? So he moved it, and all of a sudden, all the wires changed color. I said, oh, God, what have you broken? And then it dawned on me, nothing had been broken at all, because at that precise moment down in the pit, somebody had started up an experimental run, and this is real data in real time that is being seen. And it was quite good to see all the years of effort actually coming together and producing the result I was wanting. So this kind of a display then, and I'll just click through these, will update every 30 seconds. 2, 3, 1, 5. Like that, and you have a clear view then of what is going on in your complete system at any given time. Now that we have something which is recognizable even for idiots, and by that I mean physicists at 3 o'clock in the morning, we can display this subset of information pertinent to the part of the resources they are using as part of the network panel. So all of the information is gathered into one area. 2D has its limitations, though, as I already said. It's good for switch-to-switch visualization, but there's no room to put the hosts. I mean, the display is already pretty full, and I've got 3,000 processors to put somewhere. And there's no level of detail features as you zoom in or zoom out, and I can't incorporate the host details. And now we get to the bit that's, somebody said, well, this slide is all about you, Brian, and they're absolutely right. Because I want all of the detail when something goes wrong. I want neighboring views if I'm looking at individual behavior. I want the system-wide view for visual correlation. I want different levels of detail. I want fly-through. I want navigation. I want easy visibility. I want. And then it dawned on me, I was writing the specifications for Google Earth. What I want is Google Earth for my network. And I actually tried it, because they give you an editor to play with. So I built a little network, which is about the size of Belgium. And unfortunately quickly discovered that the software doesn't allow you to have dynamic data sets. It will display, 5 minutes, thank you. It will display what you need from static data sets. I want to overlay the dynamic traffic changing. So we went looking for software displays, software that does. We found X3D, which is an enhanced version of VRML. The player that comes with it is a bit clunky, so we went for a commercial player, which is the Octago player. And then we built ourselves a 3D universe whereby each of these boxes here is a functional box which retains the readout functions that we have. And then underneath them, there are the individual processors. On the top of each box, you'll see a number of features. there are panels of aggregated traffic, and there's a bezel light here, which says that it's grey if it's doing nothing, it's green if it's within acceptable limits. This is a stressed one. I don't think we have one in error at the time. The green circle behind you is using the third dimension to display the control plane. This is the control network switching, and since it goes everywhere, there's a little green pipe coming out of every box, which is the pipe to the control plane. And here we have a network, a hierarchical navigation tree, so that we can click into any of these things, or we can use keyboard system to fly into the system and see what's going on. For example, I just clicked on the control core here, and then this is showing me the red bezel. The red bezel, this is a sewage farm management principle where the big ones float to the top. So any problems lower down in the system are reflected in this light. So from a distance I can see it's worthy of attention. These are the aggregated traffic plots. This is the transmit, and these are the receive, and they're color-coded depending on the thresholds that you set for what is good or bad. And underneath you have the error lights as well. If I fly into one of the buildings of processors, I see my stacks of processors. These are grayed because they physically exist in the geographical database. And in fact, we plugged them in last week, but they've not been connected up yet. So those have not yet been discovered. These are the processor stacks, and they're all busy doing very little. This is the control switches that feed them. And if you zoom right into the front, you'll see that here's your bezel on the processor level, and the multiple units here are in fact just time displayed. You rotate them out, so when you look at it, you realize this was doing nothing, then it got busy, and then it got overloaded in the receive frame. Okay? So here's a set of conclusions, which I'm not going to go through, because if you were paying attention, you'd know what I would said. With 2 months to go to Beam, what's happening is that there's a great deal of tension at CERN. Nobody wants to be the person responsible for screwing things up. I'm old enough to believe in Murphy's Law. I know that some critical piece of equipment is going to fail. I know that some idiot programmer is going to try and send 10 gigs of Higgs down a 1 gig pipe. But I'm also sure that with the system we've built here, that I'll know about it more or less before they do and be able to do something about it. Can we now change to the video, please? So this is a screen capture of the fly-through. This is navigation with the keyboard. And so you can zoom into anything that you want. You can fly through the system. Here we're going to look at where the data sources are coming from. Here you are looking. Now here we have organized them by detector. So you can see each detector range. And you see the change in detail as you fly in. And these have actually just switched on. This was a bit of luck because we were waiting for something to happen because they were doing machine development and nothing was happening. We weren't getting any green lights. So this is not a simulation. This was a real measurement of what was going on last Friday, just before I caught the plane. And I only mean just before. What I'm trying to do is convince Octaga to use the 3D mouse that I use with Google Earth, because that's a lot smoother navigation. But I'll come back next year and tell you if I managed it. And so this is the final zoom in to looking at the actual processes. Here we've actually got one who's a bit busy. And then we zoom out and we're done. Okay, thank you very much. Are there any questions?
Off. No, it's okay. Is there any question to Brian? No? Okay, then.
Okay.
Thank you. Very interesting presentation. Our next speaker comes from the National Research and Education Network of Czech Republic. His name is Sven Ubik. I hope my pronunciation is not very well. His research interests, among others, are focused on network monitoring, optical networks, and high-speed data transfers. And for the next presentation is about this topic about 10 gigabit monitoring with PCs interfaces. So, thank you.
Thank you for introduction. So, my name is Sven Ubik. I'm from CESNET, and I would like to present you some of our results in passive monitoring of 10 gigabit lines with PC hardware. Let's first look at what is passive monitoring. There are two primary kinds of network monitoring. In active monitoring, we send test packets in the network and measure characteristics experienced by these test packets. This is a convenient way to measure one-way delay, for instance. But the problem is that the measured characteristics only truly apply to the test packets themselves. In order to find out how the network treats the real user traffic, we need to use passive monitoring, which does not send anything in the network, but it observes directly the real user traffic. Passive monitoring can provide characteristics which are inherent to real user traffic and which can't be obtained from test packets in any way. For instance, information about traffic volume, how it is distributed into protocols, what are bursts of traffic in the network, what is real packet loss experienced by users, if there are any anomalies, security attacks, and so on. The problem with passive monitoring is that it needs to process large volumes of data in real time, because we are not processing just a few test packets, but all traffic in the network. And for that reason, hardware processing is often mentioned as required for passive monitoring, because hardware processing is considered as something fast and software processing as something slow. But there is close relation between hardware and software processing, because software actually directs what the hardware should do, and we now can program even hardware in FPGAs and network processors. So the difference between hardware and software processing is sometimes said to be that hardware programming is design time, while software programming is runtime. But we now have even dynamically reconfigurable hardware whose functionality can be changed in runtime. So the hardware and software domains actually come close together. I think that the key difference which still remains is the flexibility of programming. It is still much easier to change software functionality than hardware functionality. If we look at the hardware, it's difficult to compare power of FPGAs, network processors, and CPUs in PCs all together, because they are in different architectures. For instance, CPUs now can run at much higher frequencies than FPGAs, but FPGAs can offer larger levels of parallelism. One view at the power of these devices can be if you look at the number of elementary pieces of chips like transistors. And from this view, current CPUs are definitely very powerful devices. And because higher flexibility of software programming, and because we have very powerful CPUs in our PCs, we tried to look at what we can do in software for 10 gigabit traffic in passive monitoring. Before we can process traffic in a PC, we need to transfer packets from the network to the PC memory. 10 gigabit Ethernet cards are now commonly available and they are relatively inexpensive. Additionally, there are so-called monitoring cards which look like Ethernet cards, but there are some important differences. The first difference is that some monitoring cards offer some hardware acceleration, like filtering, header classification, and simple packet statistics. And the second difference is that monitoring cards use a much larger packet buffer and transfer packets from the network to the memory in much larger chunks in DMA transfers. And in my opinion, this second difference is the most important difference between monitoring cards and Ethernet cards. We tried to test a few 10 gigabit Ethernet cards for PCI Express and PCI X buses and DAC 8.2 monitoring card, which is probably state of the art in 10 gigabit monitoring cards now. And if you look at theoretical throughput of PCI Express and PCI X buses, then you can see that in order to transfer full 10 gigabit of traffic from the network to the memory, we need PCI Express bus. There is a recommendation for throughput monitoring called benchmarking methodology for network interconnect devices, that is for routers and switches. But I think that it includes some useful practical information for testing of receive-only devices like Ethernet or monitoring cards. We tested these cards with different frame sizes spanning the regular Ethernet link range. But what's different to routers is that because a network card is not a standalone device, it's difficult to test it in isolation. So in fact, we tested a whole system. We tried to create an environment which is close to real passive monitoring applications. We use XIA generator to send packets to the network card or monitoring card, which was in a Linux PC with 2.6 kernel with standard IP stack, with NAPI driver that tries to transfer more packets in one interrupt, thus minimizing interrupt processing overhead. And we created simple test application over MAPI middleware, which did header filtering and packet counting for each packet. Header filtering was used to find service packets which we included in the stream of packets to mark ends of steps of tests. So even though we also tested a monitoring card, a DAC card, we didn't use any hardware acceleration. Everything was done in software. And this table shows measured throughput in gigabits per second for maximum zero loss packet processing. We could have reached higher throughput in some cases, but this is maximum zero loss packet throughput. You can see that with DAC card, it was possible to process all packets at all sizes without losses. while with Ethernet cards, performance was good for larger packets. So these cards can well be used for data transfers. But for monitoring, we also need to capture short packets. And at short packets, performance was much worse. The Miricom card was marginally better than the others, but the difference was small. These graphs show packet loss rate. So this is behavior after the table, which was on the previous slide. Different colors are different frame sizes. The horizontal axis is load from 0 to 100%, and the vertical axis is packet loss. And you can see again that the four cards were roughly comparable. What is interesting was the CPU load measured for maximum zero-loss processing. You can see that for all Ethernet cards, CPU was still not fully loaded when we started to lose packets. So throughput was actually limited by another component than the CPU. With the DAC card, at short packets, the CPU load was actually higher than with Ethernet cards. That was because with the DAC card, we were processing 10 gigabit of traffic in short packets. That is about 15 million packets per second. While with Ethernet cards, the packets didn't get to the PC. Okay. This picture shows architecture of a modern PC, basically the von Neumann architecture with some parallelism. In this particular example, it's a Supermicro main board with Intel 5000P chipset. What happens in network monitoring is that packets are transferred from the network card to the memory, which is commonly connected over several parallel channels, and then from the memory to the CPUs, which do their job. And the CPUs also use some more bandwidth to load the code and to store results, but this bandwidth is relatively small when compared to sustained 10 gigabit stream of data. The green numbers show theoretical throughput of individual buses, calculated just from the frequency and the number of parallel bits. You can see that throughput of these buses should be sufficient for sustained 10 gigabit processing. In practice, we can't achieve the theoretical throughput, particularly in the case of memory, when there are lots of time constraints which play a role in memory access. But this theoretical memory bandwidth can be approached in the case of almost linear access only. But the good news is that when monitoring sustained stream of data, there is a lot of linear access. And in fact, when you put two 10 gigabit DAC cards in a PC, each on a separate PCI Express bus, then you can still copy 20 gigabits of packets to the memory without losses. So from this picture, the conclusion is that in a modern PC, for 10 gigabit processing, the bottleneck can be either in a network card or in CPUs, depending on what we want to do with the packets. In our case, we saw that the CPUs were not fully loaded, So we made a hypothesis that throughput was limited by the network cards. We discussed this problem with one of the card manufacturers, and they confirmed us that there is a hardware-bound limit of about 1.3 million packets per second that the card can process, which is sufficient for large data transfers in large packets, but not good for monitoring in short packets. Let's look at how many cycles we have available for one packet. In the most critical case of 10 gigabits per second in 64-byte packets with 3 gigahertz CPUs, we have this number of cycles per packet, which is not critically bad. Some functionality can be done with several thousands of cycles. In real traffic, we have a mixture of different packet sizes. This graph shows example distribution of packet sizes from a 5-minute trace file on the SysNet GN2 link. The red part is number of packets, and the green part is number of bytes as they are distributed in different frame sizes. Roughly 40% packets were near 64 bytes, which are mostly TCP acknowledgements. 40% of packets were near 1,500 bytes, which are data transfers, and the rest was somewhere in between. So the average packet size was roughly 800 bytes. So in that case, we have more cycles per packet. And this is example of a real passive monitoring application that classifies traffic into application layer protocols like SSH, DC, GNU-Tela, and so on. It is based on MAPI and the TrackFlip library. And for most protocols, it needs to do several header filterings and payload searches in order to identify that protocol. So it's quite complex processing done for every packet. With two 3 gigahertz CPU cores, we could process roughly 3.5 gigabits of traffic per second with zero loss. And now I have 2 slides about future steps. Some time ago, the steady increase of frequency of CPUs has stopped, and now the further evolution of processors is in multiplying processing cores. There are already some manufacturers which provide processors with 10 cores. For instance, the Tyler company provides cards with 64 processing cores on a chip and 1 or 2 10 gigabit interfaces. We have one of these cards, and we are now working on how to use it effectively for packet monitoring. Okay, so conclusion is that complex zero-loss processing of 10 gigabit packet stream is possible in a modern PC when 2 conditions are satisfied. First, packets must be copied from the network to the PC memory efficiently. That is, CPU must not be loaded by this task. This is currently possible with monitoring cards, but not with Ethernet cards. The monitoring cards are more expensive, but the good news is that their cost is decreasing at a faster rate. And the second condition is that packets need to be distributed into multiple cores. So that was the conclusion, and for the second condition, the distribution into multiple cores, that can be done in two ways. The first way is in hardware. Some monitoring cards have firmware that copies packets into multiple memory buffers based on user-defined load balancing, like some hash on header fields. And they calls this DSM, data stream management, for their DAC cards. This is what we use in our monitoring for that ABW application. Unfortunately, in regular cards, which you can buy standalone, the firmware can only distribute packets into two buffers. If you want more buffers, then you need to buy these cards in so-called ninja boxes, which are PCs with DAC cards, and they are more expensive. So the second way to distribute packets into multiple cores is to dedicate one core for packet scheduler, which computes some hash on packet headers, and based on the result of this hash, distributes packets into multiple virtual buffers. I say virtual because packets are not copied to those buffers. We just need to create structures of pointers. And the trick is to do this such that flows are not split, so that all packets belonging to one flow go to one virtual buffer, because this is required by many monitoring applications. And this is what we are working on right now. Okay, that's it.
Thank you very much. Is there any question to Sven? Yes, perfect.
Do you know where in the system, where in the PC you were losing your packets? Were they NIC receiving them, or were they being lost in the IP stack?
I think that it was in the Ethernet cards themselves. I think that there is a rough limit of 1.3 million packets per second that all those cards could process. Because if we used the monitoring card, we used the same IP stack, and we could process 10 gigabit per second in 64-byte packets. No problem, no loss. So,
what we observed for, I must admit they were larger than the standard size packets, they were small jumbos, was that the operating system would schedule some other activity, and so your application couldn't receive the packets and the buffer would overflow. So you had to have very big socket buffers to get around that issue. We've seen that at 1 gig and also at 10.
okay, maybe you have that experience.
Sven Tevelin, Chalmers, Sweden. Have you done any work on the continuing problem of transferring the data you have got onto disks also?
No, we just did real-time processing and computing some statistics on the fly.
Okay, thank you.
Any more? Okay, then thank you very much for your presentation. So we finished the session. I kindly ask you to fill the evaluation form. It's available online, so you can connect to the Terena website and fill the evaluation. There is a gift, so if you fill the questionnaire, there will be a gift for you. So thank you very much, and I hope to see you in the opening reception.